Okay, so the last class, we learned how to come up with a functional expression for Boolean functions looking at a circuit diagram. We also practice drawing a circuit diagram, which is the inverse problem, looking at a function, given Boolean function. We looked at how to create a truth table and how to verify the equivalence of two Boolean expressions using truth table. So apparently, if you have two random Boolean expressions and somehow their truth tables match perfectly, that means they're equivalent. And that means there is a mathematical way using, like, obviously Boolean optimization to go from one to the other. And we will always prefer going to the like a smaller and easier expression, because that simplifies the circuit, that requires less circuit components to implement. So keep that in mind. And also something that I didn't get a chance to mention in the last class because we ran out of time is what I'm gonna talk about now. Notice it seems like a viable way to use a truth table to compare Boolean expressions and then come up with equivalent expressions, right? However, this is infeasible for two reasons. Infeasible in large scale. Initially, in terms of concept, it feels like a generic approach, which should work for any two Boolean functions. But the problem is twofold. Number one, given one Boolean function, there are literally infinite possibilities in terms of what kind of combinations you can have. If not infinite, it's very close to that, or it could be a really high number of possibilities. Number two, the more variables you have, for example, here you have three variables, A, B, and C. And I'm treating B prime as pretty much B. So I'm just considering it like one variable, all right? So you have three variables, and oftentimes these are called literals, as I mentioned, B and B prime, A and A prime. They're practically treated like a single variable and often called literal. Okay, because they're literally the same. All right, so if you have three variables or three inputs, you can have 2 raised to 3 possible combinations in terms of zeros and ones. That means you have 8 rows, and it exponentially increases as you see. If you have n possible variables or inputs, you have 2 raised to n number of rows possible. So in terms of brute force approach, it's practically not really feasible. All right, so we definitely don't do brute force. There are other approaches that we use to simplify the Boolean expression. So Boolean simplification is a very important step for logic design. So what you're learning here is the building blocks, is the fundamental principles. But people use, let's learn this together. Let's learn the building blocks. And as I told you many times, none of these are done manually today, right? You have softwares, you have electronic design automation tools that will take care of it. So these are often called synthesis tools. What you do is you code the hardware and you run it through a synthesis tool that basically takes the design that you have in terms of Boolean expressions and then optimizes it into something equivalent. So it will maintain logic equivalence. Are you guys still with me? It will go through all these steps, and chances are there is not one answer. There are multiple possibilities. So it decides on one equivalence based on what you're looking for. So when you optimize, you mention to the tool that, hey, all I care about is the absolute lowest area. So it minimizes area by all means. That means in doing so, it might make your circuit work slower, or it might take more power. So it doesn't care about anything else, just area. Or you could make it more complicated, meaning, hey, I want to optimize everything. It shouldn't have too much area or too slow or too high of a power. So that means it's a trifold optimization, more complicated. And there are other factors that we have to optimize for, which I'm not getting into here, right? These are called setup time constraints, hold time constraints. So you add constraints to the design method. If you have ever gone through any optimization process, you know the more variables you have to optimize for, the more complicated it becomes. Okay. For example, if you're just looking for a cost for a certain thing, all you have to do is look for the minimum cost and just pick that number. That's optimization. Just have one variable, you need the minimum cost, there you go. Just plot it, you get it. But if you have two variables, you now look at a 3D plot. Can you see that? You're looking at a landscape of a 3D plot, and wherever is that minima in 3D. Now, if you have one more variable, you are beyond 3D now. So you cannot even visualize the landscape anymore. Anyways, so what I'm telling you is these are all done using software and other algorithm. And this day, people are inventing new approaches for that. Okay, so we're looking at few laws per se that are used and have been used for more than a century now to optimize Boolean functions. Number one is and most of these, trust me, are going to be super simple and common sense kind of thing. So first one is associative law. What that means is if you take three inputs, x, y, and z, if you first do the AND between x and y and do the AND with z after that, it's all the same if you had done the exact opposite. Do yz first and then take AND with x. Or if you somehow can do all three together, it's going to be the same. Super simple expression. But let's notice what that means in terms of circuit implementation. So imagine you have three inputs, A, B, and C. If you do AB and take an AND, and then take C and do an AND with it, it's all the same if you do a three input AND. So three input AND basically means you are treating all three of them simultaneously. So this is ABC. And two input NAND means you have AB first, and then whatever the result for this NAND gate is, you end it with C, and then you get the final result. You take two steps. So this expression literally means you have two input gates only. This expression means you have three input gates. Are you guys still with me? Okay. And this is just my habit to connect it with something tangible. So when you, as I just mentioned a minute ago, synthesis tools, right? These are crown jewels of the industry. Without these tools, our semiconductor industry will not exist because you literally cannot optimize and simplify millions of gates together. Now, one thing that these synthesis tools rely on is called a standard cell library. You might be wondering, what do the engineers do now? Like, yes, you told us that there is a tool that optimizes it. What will the engineers do then? They will just sit and run the tool. So at some point, ChatGPT will run the tool, and then they don't need me anymore. So engineers still have a purpose, and that is to optimize the Lego. Imagine you are the company Lego. All you have to do is make those building blocks and then set it to the kids, and the kids will decide whether to make a castle or a car or whatever, right? It's up to them, but you still have to make the Lego. So as an engineer, if you make really good Legos, that means the kid can make really good stuff out of it. Are you still with me? Okay. So now, what are the building blocks? The building blocks are, as you can imagine, for logic side, gates, NAND gate, NOR gate, XOR gate, blah, blah, blah. But don't feel like, oh, there are just a few gates. There are different flavors of NAND gate. There are two input NAND gates, three input NAND gates, four input NAND gates, and they have pros and cons. You might be wondering, if I could take and handle three inputs at a time, why would I even bother having two input gates? These are design decisions, and I'm not getting into the detail of it. I'm very tempted to. So the more inputs you handle simultaneously, the slower the things get, the slower. And we explained that in 433. Literally, we compare between, so if you see a diagram, a plot, this is propagation delay for high to low switching. Literally goes up like this with n being the number of inputs. So the more inputs you handle simultaneously, the slower the circuit becomes because the delay goes up. Okay, there are reasons, we discussed this, but for now we're just going to ignore it. But know that yes, I mean, this thing is a design decision. You might have to use four inputs because it might simply become too area expensive. Anytime you break something into multiple components, it's going to take more time versus something that is integrated. So if you have a four input integrated gate, it's going to take less area, but it will be slower. You see that, folks? Okay, so this standard cell libraries have flavors of same gate, two input, three input, you name it. Some of these gates are optimized to be extremely low power. Some of these gates are optimized to be very fast. So all of these designs are done manually by the engineers. So you are an engineer in charge of making NAND gate and only two input NAND gate. Your friend is in charge of making three input XOR. Your other friend is in charge of making four input NAND. So there are like 100 engineers who are designing 100 different circuits, and all you do, you get up, you go to the office, design two input NAND. I'm oversimplifying it. Obviously, you don't just do one thing, you do a number of things, but that's your responsibility. If something goes wrong with the NAND, they're going to come after you. Hey, your NAND is not working properly, right? Okay, so you make sure that you make it an art, basically, like you make the best NAND ever. and then you add it to the standard cell library. So all hundreds of engineers that are part of the company, they all contribute to the standard cell library. And then the tool literally uses them like Lego. The tool decides, hey, if I take 2 input versus 3 input versus 4 input, will that make the overall delay? Not just delay for one gate. Maybe you're sacrificing one gate to win in the bigger picture. Okay, so it basically picks and choose, and that's where billions and possibly trillions of combinations are possible. So that's why you need the tool. You cannot manually do it. Simply cannot because of the number. Are you still with me? All right. So these are all design decisions. We just have to know about them that, okay, this is a decision, but the tool will handle it. The exact same thing applies to the other version of this for OR. So if you do OR between X and Y and then do Z, versus if you had done the opposite, it's all the same, doesn't matter. And if you handle all three of them, it's basically the same. And that reflects in the circuit design as well. Instead of having two stages, you have just one stage. All right. Now, let's move to the next one. These are some useful, theorem is a big word, but it's okay. These are kind of like theorems that we often use. And most of these are common sense. And I will show you a couple of them as to how it comes into being. So if you have xy plus xy prime, meaning the true and complementary version of a variable being attached in AND formation with another variable, you could literally ignore that variable and come up with just the one that was left. Okay, but you don't have to memorize it this way. Here is how you can also calculate it. Notice, you can take x as common and you can have y plus y dash. You see that? What is y plus y dash? Thank you. Yes. So a plus a dash, which is like you are basically unifying the entire possibility. It's either a or a prime. Between a and a, whatever is not in a is there in a prime, and whatever is not in a prime is there in a. So together they formulate everything, which is 100%. So y plus y prime is basically 1. So you are left with x. Okay. Similarly, let's take an example of this one. X plus xy equals x. So you could just take x as common and you're left with 1 plus y. 1 or everything. So if there is one in the OR operation, you just need 1, 1. That means the result is always going to be 1. You don't care what y is. It's either going to be 0 or 1. Doesn't matter. The output is going to be always 1. So you're left with 1. So most of these could be just calculated with this couple of steps. Some of these are not too so intuitive, but most of these are. So you can use this to calculate and optimize logic functions. And now I'm not worried about this small scale stuff. Oftentimes we have more complicated expressions and we try to map it to some of these equations to quickly simplify them. Otherwise it would have taken us more time to do so. This is one example. Let's see this together. So you have an expression that apparently looks a little bit complicated. We are trying to simplify it. And the way you could do it, you notice this portion is being repeated twice. So we could just treat it like an x. And this portion, again, is being repeated twice. We could treat it like a y. So what you're left with is a form that looks like x plus y and x plus y prime, which we have an expression for. It should be just x. So you simplify it to just 1, a plus b prime. So it's a fast process. But just let's hold on a second. Do you think it's a very efficient process to do it manually? No, like let's see which one. And if I change one thing, just notice, if I just make one of them different, G, it's no longer applicable. It's no longer applicable. Done. There you go. So it's not as easy as, oh, things are not going to fall in place in real life. In math question, in your homework, in your quizzes, I will make sure that you find a form, right? That you can match and simplify. But in real life, when you're trying to map real problems to Boolean expressions, you're not going to end with a really nice ideal expression that looks like this. Okay. But there might be one. It's very difficult to manually match. That's why you have powerful software. Okay. Now, any questions so far? Do you see how we use this theorem to somehow simplify a seemingly complicated expression into something smaller? Yes. Great question. It means the complementary version. So if you have x, x prime means basically the invert of x. So if x is 0, x prime is going to be 1. Always. So invert. There is another, get used to this, depending on which textbooks you are reading. X prime means exactly the same, bar. And in some textbooks, which are very rare, people used to use tilde, this sign, tilde, right? But typically, for the most part, people try to use x prime. It's easier to type. Just imagine, bar is not that easy to type all the time. Okay, so yeah, this is what we covered. Please let me know if you have any questions. Okay, we are heading into very important a couple of very important terminologies that we all need to learn for digital logic design. Number one, sum of product form. And the other one, as you can imagine, would be product of sum form, exactly opposite. And before these are for you to read later at home. I'm going to explain it anyways. So I'm not going to go through this. Just take a look at one expression. This is a Boolean expression. So f equals this thing. Can I literally just take the language and see, hey, it's a sum. So that's why you have plus of different products. Do you guys all see that? So it is a sum of product form. Let's go back to the previous thing that we have optimized, this one. Do you think it is a sum of product form? It is a mixed form, actually. Like, I cannot categorize it to be a sum of product or product of, like, product of sum, because there are some rules that we have to follow. Number one, in a sum of product form, you have every variable or every literal appearing just once. Okay, so you have a, b prime. These are independent literal. C, d, e, a, c, e prime. So in every term, you just have one of each. A, c, b, just one of each. You don't have a, b, c. Does that make sense? What if I had a, b, c? You basically write it a, b, c, because a is literally a. That's another equation for optimization. Okay, so you bring everything down to the form where you can no longer reduce these individual forms into anything else. This is the minimum individually, not as a whole. Individually, these are the minimum. Okay, so you have these forms, and then all of these forms are ORed with each other. So that's the sum of product form. Let's take some other examples, because I get these questions. That's why I took these examples and said them, like, spell them out. What if there is just one variable somewhere sitting, which is possible, right? This is fine. This is also a sum, although you don't see a product here, but feel like there is a product like this with one. So it's still treated as a sum of product form. Remember, it's not about the language per se. It's about how we implement these expressions in actual hardware. That's when things will become clear. Trust me. So, bear with me for a few minutes. So that's why even if there is just a single variable sitting somewhere, which is seemingly not a product, it is still qualify as sum of product form. If there was another question at some point, what if we have multiple variables that are single? Yeah, sure, all the same. And then there is a product. Still with me? Okay. And what an example of what is not sum of product, this one. So this thing is fine. I don't have any complaints against it, but this is not sum of product. How can you convert it to a sum of product form, folks? Just multiply them. Yes, you get ACD plus BCD plus EF. Now this is a sum of product form. Okay? Trust me, there are reasons to discuss this seemingly simple stuff. These simple stuffs make really big decisions eventually, hardware decision. And don't worry, you don't have to wait for 433. We'll cover it here in the next slide, actually. Okay, so let's take an example of how to convert a regular expression, which is this one, to this. Interestingly, this is not sum of product, not product of sum. This is a mixed expression. Okay? And when we see product of sum, you will understand why it is not product of sum. And let me just point out, because of this term, it's not a product of sum expression. And we'll see what I mean by that. Simply because of this is the culprit. Simply because I have BC here, it's not a product of sum expression. Although it looks like product of sum, but it is not a product of sum format. Okay, in terms of our standard. Okay, so what we do is we basically multiply everything like this, like multiply. Okay, why do you see an A here? Can anybody guess? Yes, thank you. When you multiply A and A becomes A. So, and similarly, you just keep simplifying using the theorem we talked about, and you keep simplifying. Apparently, you end up with this expression. This expression is the sum of product form. So many a times you'll find yourself reducing down Boolean functions, which are random. First, you come up with a function based on real life correspondence. You see a real life event, real life system, you convert it to a Boolean expression. Then you simplify it using either sum of product approach is a direct analog to hardware implementation. I'll show you. But before that, let's talk about product of sum first. Product of sum is, can anybody notice this expression and tell me what do you see? Like any comment? Why did I go after BC in the last expression? I told you that because of that, it's not a product of sum. Notice in every term, one variable or literal appears just once. It's alone. There is no product anywhere. A or A prime, B or B, just one at a time. No product. Do you see that, folks? And then they are summed together. Sum in basically means or here. So sum, and then product. So you have product of sum. Does that make sense? You're eventually taking a product, not sum. Whereas in the previous case, you are eventually taking a sum. You had products and then you are summing them. Here you have sum and then you are taking the product. Okay, that's why it's a product of sum. More example. This is fine, this is fine. This is just a single variable. There is no sum per se. But we could always treat it like, let me show you. We could always treat it like f plus 0. Anything plus 0 is that thing. Are you still with me? Okay, so it's still a product of sum format. So is this one. So each of these variables could be individually converted into a format like this. So it's still a product of sum format. What is not a product of sum format is this one. Why? Notice, I mean, you don't have to look at anything else. This is killing it. And then you have a plus here. It's not really a product of sum. Okay, so you have to just break it down. And getting to a product of sum format is more complicated than getting to a sum of product format. Are you still with me? I mean, it's not like for sum of product, all you have to do is multiply everything, like make them flat, and then try to optimize, reduce things by taking something common or using some theorem, and there you go. You're left with the bare minimum. That's product, sum of product. And trust me, that's the more widely used approach, by the way. Okay, product of sum is the opposite. Given a random expression like this, sorry, this is the expression, you use some tricks, and the tricks are mentioned here. So there is nothing special about this particular example. If you move to a different example, you'll have to think all over again. There is no standard way to do so. So you have to be mindful of all the available theorems and try to bring in extra term. You just add extra term here and there and take things common and apparently end up with an expression that looks like this. More complicated, don't you think? So honestly, in most cases, these are no longer used. You might be wondering, why did people even use this? Really tempted to go to tangents, and maybe I can take a tangent here. History is important. So there was a time in semiconductor industry where you could make just one kind of transistor. We have two types of transistors now. They always come in pair: NMOS, PMOS. Have you used any transistor for any of your projects ever? MOSFET, one lab. Yeah. Do you know whether you used an NMOS or a PMOS? Probably you didn't even pay attention to what type of MOS it is, right? This is obviously understandable. So, typically you either use a PMOS or an NMOS. Okay, there are two kinds. They're like almost similar, except they're complementary to each other. They're complementary. That's where we often use the term CMOS. C stands for complementary MOSFET. So the reason why we call CMOS is because we have complementary devices. But there was a time when we didn't have this. Okay, so remember, if you go for one specific type of design that favors PMOS or favors NMOS, one of these sum of product or product of sum will be your to-go place. Okay, so imagine you only have one kind of transistor that could support product of sum. So it doesn't matter if even if it is more complicated to handle, you'll have to live with it. But not anymore. Now we can make both of them with extreme efficiency, so we don't care. We'll always go for the easiest approach. Which one do you think is easier to handle? I didn't even care to explain what we're doing because it's so random. You're just, cherry picking. Can I add this term, that term here and there, and somehow come up with an expression that looks like this? This is more difficult than if I gave you this expression in the first place. All you have to do is just multiply everything, make them flat, and get to this, sum of product. That is, in my opinion, simpler. Okay, anyways, big reveal. Okay, now is the big reveal. Why do we care about sum of care and sum of product and product of sum? Let's see. Can anybody help me make the function here? What is this? Let's work together on this. This is an AND gate. So you have AB prime. Here you have C D prime E. Here you have A C prime E prime. And then what do you have eventually in the function? Add all of them, right? So basically, this is going to give you something plus something plus something. So it's a sum of product. Notice in a sum of product, you always add things last. So you take ends in one stage, and then finally you add all of them together. This is a design approach. Okay, I'm going to get back to this. Let's do one more practice. How about this one? What is this expression? This is going to be D prime E. And these are just independent variables. So you're going to be left with A plus B prime plus C plus D prime E. Do you think it's the sum of product expression? I just told you. Yes, it is. So again, as long as you have a big OR block sitting in front and merging everything together, that's going to lead to a sum of product expression. Are you all good? Okay. Let's finish the rest as well, and then we'll get back to collective discussion with both of them. So this is a product of sum discussion, as you can imagine. Let's still see, what is this? A plus B prime, because this is an OR gate. It's going to be A plus C prime plus E prime. And this is C plus D prime plus E. And this guy is going to give you the product of all three. Make sense? So you're going to get a product of sum. Don't you think they look similar? I mean, in terms of footprint, in terms of similarity, you either do AND later or first, or exactly the opposite. So it's a design decision for hardware engineers, and you can do the other one as well. Now, notice this: both of these approaches have one thing in common. Both of these approaches have one thing in common. They break any Boolean function into two stages. Do you see that? In one stage, you either do all AND, and the final stage just has one gate where you do an or exactly the opposite. So they simplify and make things uniform. Okay, there is an advantage. Are you still with me? Now, I'm tempted to go back and show you one circuit that we worked with together. How about this one? Do you think this circuit resemble anything like this sum of product or product of sum? No. This is a Boolean logic circuit. But the function that you get out of it, for example, this one, this is already there. This function is already there. Is this a sum of product or product of sum? No. So not all Boolean circuits will be giving you product of sum or sum of product. You have to work for it. Okay. Are you still with me? But can you feel that given a Boolean function, you could always reduce it down to a sum of product or product of sum? Product of sum, I told you it's more difficult to get to, but theoretically it's possible. But sum of product, you can be confident. Just multiply everything out. Don't even think about it. And then whatever the bare minimum you're left with, it's always going to be sum of product. So you could do something with it and convert this circuit chain. This is a chain or pipeline circuit where things are driving each other. And the other one is like a hierarchical circuit. You have one level that is feeding into the second level. Done. Two levels. It's always two levels. Okay. So you could always convert this circuit to the circuit that I showed you. Yes. Great question. It's not really a buffer, it's an inverter. So buffers, I mean, we are not discussing that here, but buffers are often they're there, you don't see them. So oftentimes there are do you guys remember what a buffer is? I think you meant to say inverter, but I'm still gonna address that. It spits out the same thing, 0, 0, 1, 1. So input and output are exactly the same. Why would you even use them then? They're used to regenerate signal. So when you have a pipeline of circuit, signals degrade. So initially, if you provide 5 volt, you end up with 4.8, 4.5, 4.2. Gradually, as you go through the chain, the voltage levels will degrade. So you insert buffer, and the buffers take all the way back to 5. So buffers regenerate. And that's literally a lecture in 433. It's called regenerative property of CMOS circuits. We'll talk about why they regenerate things. So something degrade, you put in a buffer or a CMOS inverter, regenerates the voltage and takes it back to the full level, right? But here, first of all, you may or may not, we don't know. But when you convert this to sum of product, you will not need the inverter anymore, okay? Or product of sum, you'll not need. They are structured literally to use two kind of logic gates, AND and OR. Still with me? Okay. So you see the promise there. Do you get, this is called standardization. You make sure everything looks exactly the same in terms of architecture. So you have a template that you follow per se. Do you know? This is the last slide of this lecture, okay? But I'm going to take a few minutes to talk about this. Do you think this is called standardization, so that everything that you design looks exactly the same if you want it to. But if you don't go for this approach, it's fine. But if you go for it, I know exactly how your hardware is going to look like, okay? So if I am reverse engineering, what I'm going to do, I'm going to look for the last OR gate and see what it is adding. So these are definitely going to feed into all these other gates. And then I'm going to look for all the ends. So basically, I can easily spell out the function quite easily. So that's the challenge, because it is so uniform, anybody could reverse engineer. But also, it is so uniform, it is easy to mass produce. Okay, just imagine. You make an accessory, like a phone cover, that fits Android, iPhone, all other kind of phone. You can sell more. You could sell to the Android users as well as Apple users, don't you think? So universality or standardization has its merits. It allows you to basically cater to the needs of multiple applications. But if you custom design, like the circuit that you saw, the pipeline, that was custom designed for a given Boolean function. You cannot reuse that format for anything else. So if you are a company that makes a small part of the circuit and you keep making this sum of product format hardware, okay, if I give you more inputs, you just put in 0 or 1. Does that make sense? Or just keep them floating if you want to. We don't keep them floating, but apparently you could just do something with it. You can always make all the logic layers 4 input, 4 input, 4 input, and final OR gate 4 input. Say that's like an FPGA, for example. Programmable, you could use it for whatever you want to, control. But I'm gonna just make this circuit forever. It's easy for you to make. Versus if you need to custom make every circuit for every application, it's gonna take more money and more efforts. Okay, I hope you at least had an idea about what it means, but we'll hear more about these two products and basically interconversion between them. Let's head to the next lecture, at least get started. And we'll not be able to get too far, but let's at least get started. So literally the lecture is called deeper dive. So you're going to take a deeper dive into the Boolean operations per se. Are you guys feeling lost? Okay. All right. So I want to cover this. It's easy enough things to cover in like 3 to 4 minutes. That's why. It's a theorem. I mean, you don't feel like you have to memorize all these theorems. This will become like habit for you. Like after you go through this course, if you like do a few homework, practice a bit at home, this will be like natural. So what is consensus theorem? Okay, I will start with the example first, and that simplifies it. Just look at what we have here: xy plus x prime z plus yz. Just observe something, all right? Notice. And then apparently, I optimize this to have only 2 terms. I'm going to take a step back and let you think about how that translates to the hardware. Going from this format to the optimized format, reduce what kind of format is it? If I try to implement that in the format that we just discussed, can I use that AND gate, AND gate, AND gate, and then OR gate format for this? Okay, when you get rid of one of the terms, what will it reduce? Folks, it will get rid of one of the branches, and it will make your 3 input gates a 2 input gate. And that is a significant saving, by the way. Those additional input gates don't come for free. Are you still with me? Okay, so you see, immediately, just by reducing one term, you significantly simplify the hardware. That's why it's a big industry. Okay, all right. So my point is just notice xy, x prime z plus yz. In this situation, let's observe something. X and x prime are both in an AND relationship with y and z. And you also have a product of these 2 variables that were both coupled with x and x prime. In this situation, the other term is redundant. You could just get rid of it. That is the theorem. That is basically the theorem. And this is the proof of the theorem. I'll show you the proof later on. What is that? Let me show you. Let's draw something from scratch. So imagine you have a plus a prime. Okay, and you have a variable g connected to a and d connected to a prime. And then you also have a term which is gd plus. Okay, what this theorem says is gd could be ignored. It is a redundant term. Just get rid of it. Okay, does that make sounds like a very specific? Will we ever run into this? Yes, we do. Many a times we end up with situations where 2 variables are coupled with that what we call a true and complementary form of the same variable. True form, complementary form. Okay, invert of a variable is called its complementary form. So if 2 other variables are linked with true and complementary form of the same variable, you could literally get rid of the product of that if they appear. Okay, so the way we prove it is by adding redundant term, as you see. Basically, before yz, we introduce a term called x plus x prime, which is essentially 1. Do you know that? X plus x prime is essentially 1. So we're not changing anything. Then you multiply it, you group them together like this, and apparently do some Boolean optimization and end up with this. Take a look at it at home. If it doesn't make sense, I'm more than happy to go over it. Okay, but don't feel like you have to prove everything, prove all the Boolean theorem. If you are curious, take a look at it. That's why I put it there. Super simple stuff. But we'll be using this quite often in the actual hardware optimization. And by the way, there is a dual form. This is for product, right? You have a similar format of consensus theorem in terms of sum like this. Notice you have x plus y and x prime plus z, and then you have y plus z. So something is ORed with the true and complementary version of the same variable. So y plus z will be ignored and redundant. So just take a look at it, think about the theorem, compare this one with this one, and you'll see they are kind of similar. You can prove it in a similar approach, and we're going to use it quite often for optimization. Okay, so anyways, this is a different topic. I'm not going to get into it now because there is a big break. So on Wednesday, which is a long time from now, we'll talk about this. All right, I'll not review this consistent anymore. Please review it and let me know if you have any questions. Thanks again. Have a great long weekend.